we're going to take a look at some data about penguins using box plots. Now, the penguins data comes from the Palmer Penguins package for R by Horst, Hill, and Gorman. It contains, for the variable we're going to look at, which is bill length, 342 measurements of penguins from 3 different species. As you can see, the species are chinstrap, gentoo, and Adelie. There's 151 Adelie. That makes them the biggest group. Chinstrap is the smallest with 68, and gentoo has 123. So they're uneven-sized groups. So let's investigate the question of whether the bill lengths for the 3 species differ. And in doing this, we're going to build our way up to using box plots. So to start off, let's say that bill length is a quantitative variable. It's measured with 1 decimal place in millimeters, ranging from 32.1 to 59.6. And you can see that the bill length is basically the horizontal size of the bill. If we sort the observations, the penguins, by length in order from low to high, the lowest 20 observations would be starting at 32.1 and going to 35.7. Notice that there's some duplicate values, like the last 3 values are all 35.7, and that there's also, because of the decimal place, there's a lot of uneven spacing between the points. So sometimes 2 points next to each other, of course, might be the same. They might differ by 0.1 centimeter, like from 34.4 to 34.5, or they might differ by a whole millimeter, like from 32.1 to 33.1. Here are the last 20, so these are the highest 20. And again, we see the same issue of multiples of some values and uneven spacing. And then we could look at the middle 20 observations. And the middle 20 observations are interesting because, of course, we're often interested in the center of the distribution. So these are from 161 to 180. And the 2 actual exact middle observations are observations 171 and 172, which are 44.4 and 44.5 millimeters, respectively. So remember, we had 352 measurements, so it's an even number. So there's not one middle value. We have to look at take 2 to find the middle. This dot plot is a way to display the data, which showing most of the data points, despite the fact that there are many of them that are extremely close to each other, and many duplicates values. So what's interesting about this is that it's just got data across one axis, the horizontal or x-axis, which shows bill length. And then the height of the points, where the points are located vertically, does not matter. It's just, this is a way of just showing you as many points as possible. And they are basically letting us see how the data cluster, and then we also can notice that, say, especially up at the high end, there's a little bit of small number of observations. The density gets a little bit lower as we go high up to that high part and end up at around 60. This is another way to present the same information, also called a dot plot, but this takes a slightly different approach. It obviously turns them into something like a histogram or bar chart, and it's essentially has rounded the numbers so that they all fit into a finite number of columns or stacks. So there's in some ways it's easier to read, in some ways it's sharing less information. We also can notice, though, that here there are some specific rounded values or bins that have a large number of observations. We can see them basically in between the biggest one is about halfway between 40 and 50. And there's also a smaller one just above 50, and then kind of a less well-defined one down around 40. So one thing we can do right away to try to understand this data is to divide the data in half and see what's the, what does the bottom half of the distribution look like? What does the top half of the distribution look like? So we already mentioned that 44.4 and 44.5 were our two middle values. And one simple and commonly used way to do this is to kind of split the difference between the two of them, add them together, and then divide by 2. In this case, it would be 44.45. However you do this calculation, it's known as the median, or it has another name that we'll see later, the second percentile. Of course, we can't really see the level of detail represented by 44.45 here because this is just, that would require a really big graph in order to be able to show those exact spacings. But the dot plot does try to more or less organize it so we can still see the points. Okay, so now since we are interested in the species, we can color the dots with the colors corresponding to the species. And this helps us see that maybe there is some kind of relationship between the species and the values of bill length. So just looking at it, eyeballing it, I can see that most of the adeles are in the lower half. And there's only maybe one adele or two, there's a hidden one, I think, there that is in the upper half. And so that's interesting. Maybe adeles are different. On the other hand, the chin strap and gentoo are all kind of mixed together there. I'm not sure at this point I see any structure to that. I see pretty high values for both. I see low values for both. So I don't, I'm not seeing any clear structure differentiating those two. So as a next step, what we can do is divide it further. So we can divide it, instead of 2 parts, we can divide it into 4 parts. And how do we do that? The first thing is basically to do the same thing for the bottom half, the bottom 171 points, as we did for the whole data set. So find the middle value, which in this case would be observation 86, which has a value of 39.2. Now notice, because it's an odd number, 171, we get an exact value. And then the top half also has 171, so we get a middle value at observation 257, and that has a value of 48.4. So these values are, by doing this median followed by 2 medians of the smaller groups, we're dividing the data into 4 even-sized slices, and these are called quartiles. Quartiles being like quarter, 4. The lower one is called the first quartile. The median can be called the second quartile. That's the median of the whole data set. The upper one is called the third quartile, and then we didn't plot it, but the maximum value would be called the fourth quartile. But that's just, not necessary to plot because we just know it's at the highest value. So, and then there's something called the IQR, or interquartile range, which is a fancy name for saying take the third quartile, 48.4, and find the difference between that and the first quartile, which was 39.2. So if we subtract them, we get the interquartile range of 9.2. So now I'm going to go ahead and add my quartile lines to the plot. Again, this is pretty interesting. It kind of confirms my earlier observation about the Adelies. The only species in the lowest quartile are the Adelies. Most of the remaining Adelies are in the second quartile, but there are also mixed in a smaller number, but still present, of the chinstraps and the gentoos. Then in the third quartile, we see kind of a mix of chinstrap and gentoos and the two larger Adelies. And then in the fourth quartile, we don't see any Adelies, and we see a kind of mix of the other two. So this helps us to kind of clarify that maybe there's something going on with the Adelies. So what has all this got to do with box plots? So the top image here is showing a box plot, and the bottom image is just a smaller version of the graph we just looked at. And basically, a box plot is a way of displaying information about data developed by the statistician John Tukey, and he was an advocate for methods of data analysis that utilized visual approaches to understand data. So in a box plot, the box is a rectangle bordered by the first quartile on the bottom on the left side and the third quartile on the right side. And then in the middle, there's a thicker line that represents the median. So you can see that those lines, the edges in the box plot, align with our quartile lines from the previous graph. So make sure you see that. Then what the box plot does for the first quartile and the fourth quartile is extend a whisker. So these are sometimes called box and whisker plots. So the lines sticking out are called whiskers, and in this case, they extend to the maximum and minimum values. That's not always the case, but in this case, that's what happens. So that basically tells us that they're not really any wildly out of the range values. You'll see why in a second. So here we can see what is maybe a more interesting use of the box plot, which is to introduce groups by a second variable. So in this case, the species, and use that to create box plots for each of the species. And we can compare the species to each other. What's nice about box plot is that we can see both that the medians are different for the three groups, and that for Gentoo and chinstraps, the medians are somewhat close to each other. They both, if we drew lines up and down from them, the medians would fall within the box for the two of them. But for the Adelie, the median is well below. The median is actually below the lowest values of the Gen 2s and the chin straps. So in other words, if you drew a line straight down from the endpoints there, of the Gen 2 and the chin strap, you would not run into the box for the Adelie, and you would not hit the median. And so that means that the overlap is really in the upper quartile for the Adelies. On the other hand, the boxes for the Gen 2 and chin straps are very close to each other. So we could make, on the basis of this, all kinds of statements like that 75% or more of the Adelies fall below 75% of the chin straps and Gen 2s. Now, how do I know that? Because the right-hand edge, the upper edge of the block for the Adelies represents 75% of that species, and the left-hand lower edges of the blocks for the Gen 2 and chin straps represents either the bottom 25% or the upper 75%. So I can say that 75% of the Gen 2s here actually fall above 75% of the Adelies here. And the same thing for the chin strap. 75% of the chin straps are above 75% of the Adelies. We could also make a bunch of other statements about these distributions. We could talk about that none of the Adelies are above the medians of either of the other two species. We could talk about the size of the interquartile ranges. We could talk about the maximum minimum values. There's all kinds of interesting things that we could say. We could also say that the Gen 2 and the chin strap don't really look that different from each other. Now, what do we notice that's really different than we saw previously? For the Gen 2, we see a dot over on the far right. What is that? That dot represents what we call an outlier or extreme value. So how do we determine that a point is far enough to say it's an outlier? Well, there's different rules that people use, but we'll use Tufte's, and we'll say that the box plots will extend the whiskers to a maximum of 1.5 times the IQR, or interquartile range. So it's just going to sound like a lot of multiplying and subtracting and so on, but that's okay. So for the Gen 2s, the IQR is 4.25. So 1.5 of 4.25, we take 1.5 times 4.25 gives us 6.375. The third quartile for Gen 2s is 48.5. So the maximum for the whisker is 48.5 plus 6.375 equals 54.875. The maximum bill length for the Gen 2s is 59.6. So therefore that particular penguin is beyond 1.5 times the IQR, so it gets a separate dot. On the other hand, the chin straps don't, they also have some similarly long bills in a couple of cases, but their IQR is a little bit bigger and their median is, their box is a little bit to the right. So in that case, the high values don't end up producing an outlier. This is just a rule of thumb, but it does make us start to think about, why do we have an outlier? Is there something special about that? Was there a data entry error, or Was that just a result of chance? There's a lot of possibilities. The good thing is that even though there's a lot of multiplying and dividing and it seems like you have to use a calculator, you don't, because fortunately these days we can use software to create box plots. Here you can see we've added the representation of the original points to the box plots, and this can help us see a little bit better how the original distributions work. For example, we can see how the points within the whiskers are distributed. We can also add points to the plot to illustrate the actual data used, and this can be a useful way of understanding what's happening with the data. One of the things to remember, though, when you look at data displayed in this way, is that many of the points are hidden. It's not showing you the individual points. It's just giving you a sense of where there are big clumps of points because of the values being the same or very close to each other. So what kind of conclusions can we make? In terms of whether bill lengths of the species differ, my tentative conclusion is that the adelids do have shorter bills than either of the other two species. However, the gentoo and the chinstrap bill lengths do not meaningfully differ. If I spotted a penguin with a bill length of 40, I would feel pretty confident guessing that it is an adelie. If I spotted a penguin with a bill length of 55, I would guess that it's not an adelie, but I would not want to have to guess whether it is a chinstrap or a gentoo. And then overall, box plots provide a rich way to visualize distributions because they simultaneously show the center and the spread of the distributions. Box plots encourage us to notice the presence of outliers. This can lead to exploration of why outliers are present and consider which kinds of statistics would be the most appropriate use for further analysis.